This is text problem 9-33, one of the suggested problems for lesson 16. So as we read through this problem, there's a couple things to highlight. We have our mass here, an initial velocity in magnitude and angle form, and we have a final velocity in magnitude form, and the direction is straight up. We also have an overall time of the collision, or duration of the collision. So this should, as we go into our read step, let us know that this is an impulse problem. Being able to identify the type of problem you're working with will help you on future WPRs and the T, as we have more and more concepts piling into your backpack full of physics concepts. So our drawing is already done for us. As we look at our givens, we're given the initial velocity in magnitude and angle form. And that is with respect to the negative x-axis, as shown in the drawing. We're also given a final velocity, v2, and I'm going to go ahead and use unit vector notation. And we'll break down our initial velocity here in a second. So to break down our initial velocity into its components, we use our drawing, and we see that we have a triangle where our hypotenuse is the initial velocity, and our x component, or horizontal component of the velocity, is on the adjacent side, and the vertical component is on the opposite side of our angle. So, and this is all with respect to these coordinates as seen in the drawing. So the velocity in the x direction for our initial velocity is our hypotenuse times the cosine of the angle, because it's on the adjacent side, and it is traveling in the negative I hat direction. And the vertical component of our initial velocity is our hypotenuse again, times sine of our angle, because it is on the opposite side of our angle, and this is in the negative j hat direction. So for our assumptions, we don't have any for this problem. But for our tasks, we have quite a few. First one is to find the magnitude and angle of our impulse vector, and that angle is with respect to the positive x-axis. Part C and D is to find the magnitude of the average force on the bat and the angle also with respect to the positive x-axis. And our physics for this problem, we'll be using our impulse equation, and that's in vector form. We'll be using the magnitude of our impulse equation in terms of the average force, and just in general linear momentum of a single particle or object. So as we move into the solve step, we're going to start in part A with finding our impulse vector, and we'll break it down into magnitude angle here shortly. So we have the total change in momentum, and since both our final and initial momentum share the same mass of our baseball here, we can distribute that out. And our final velocity is velocity 2, and our initial velocity is v1. So the effort we put into putting our initial and final velocities in unit vector form will help us here. As we break it into final minus initial, so I have my final minus initial in the I-hat direction, and my final minus initial in the y direction, or the j-hat direction. So as we continue, we remember that our final velocity had no horizontal component. So that goes to 0 minus our initial, which was v1 cosine of our angle. And here we do have a vertical component, and it was entirely the final velocity, or the magnitude of velocity. And our initial velocity and its y component was the magnitude of the initial velocity times sine of the angle. So now we can put in our given values, our mass, our final, minus our initial in the I-hat direction, and our final minus initial in our j-hat direction. So now we have our final minus initial velocities in our unit vector directions, and now we need the magnitude, so we take our x component of the velocity and y component of our change in velocity, square each of them individually, add them, and then take the square root. Now as we work through the magnitude of our impulse vector, it gets us through part A with 5.86 kilogram meters per second. So for part B, we need to find the angle of our impulse vector with respect to the x-axis. So we have our angle is equal to the arctangent of our y component versus our x component. Now within our impulse vector, the only portion of that vector that has directionality is our change in velocity. So we can put the change in velocity, y component, over the change in velocity for the x component. Now looking at this in the form of a triangle, we have our angle, we have the y component of our impulse, and the x component of our impulse. Again, the only portion of the impulse vector that has directionality is our change in velocity vector, which is what we have in this upper portion. So that is equivalent to, sorry, bad triangle. Again, that's equivalent to saying the change in velocity in the y direction, change in velocity in the x direction, where here's our angle. So we're looking at the opposite over the adjacent, which leads us to our tangent function. And we finalize that, and we get 59.8 degrees with respect to the positive x-axis. And there's our answer for part B. So for part C, we get to find the average force on the bat. So we have the magnitude of our impulse is equal to the average force times the change in time or the duration of our collision. Well, we have the magnitude of our impulse from part A, which I have up here in the top right. And we're solving for the average force on the bat. So we do some algebra to rearrange our equation, and we have the magnitude of the impulse vector divided by the duration of our collision. And that results in 2.93 times 10 to the 3 newtons. And that completes part C. And for part D, the angle of our impulse vector is the same angle as the angle on our average force. The reason being is that the only external force that is creating this change in momentum over time is the force of the ball on the bat. And the direction of that impulse is the same direction as the force of the ball on the bat.